Okay, so we have we've been looking at the parametrically driven oscillator, and again the working conditions are the oscillator has a nonlinearity. It's driven parametrically in the sense that this looks like we are modulating the frequency of the pendulum. If it is a pendulum, this would correspond to the case of modulating gravity, and we have the conditions for our for getting quantitative results. Brings certain degree of approximations. We have weak damping as a basic assumption, where weak damping is determined by or expressed in this fashion, that the lambda is much less than omega naught. The nonlinearity is weak also, and that is quantitatively expressed this way: the magnitude of alpha times a squared, which a is the excursion of, say, the pendulum, is less than omega naught squared. And we have weak drive. The excitation amplitude is weak. As we get into the demo today, you'll see that none of those assumptions are actually met. But qualitatively, every result that we are going to be getting is qualitatively well represented by the pendulum. There is the damping is not weak, because look, it takes only a handful of oscillations for the system to decay, where you're going to see as I drive it that say in the small amplitude regime, you can actually see the excursion of the cone is comparable to the length of the pendulum. So it's the amplitude, the drive amplitude is not weak either. And the nonlinearities you're going to see, like right now, that amplitude is not necessarily small, okay? So all the assumptions that we have there are good to get answers, quantitative answers, but the demo is not going to quite represent them. But qualitatively, everything that we get on the board is going to be in the demo. So we derived yesterday, or in a couple of days, the conditions to excite the pendulum from rest. And we have to say if the pendulum is at rest, what is the minimum drive amplitude that is, if a fluctuation appears, say, is going to bring this into steady motion, and or into what is going to make the amplitude grow from rest? What happened here? Okay, what is going to bring it to that state? And so we determined that the condition to drive it from rest, due say to fluctuations, the parameters that would make the amplitude grow from an equilibrium point, which is rest, is determined by this condition. The drive amplitude, which is weak, which is a small quantity, has to be greater than epsilon over omega naught squared, where epsilon is the difference between the frequency of the drive, half of the frequency of the drive, and the natural frequency of the oscillator, and that difference is itself small. So this is a small parameter, it has to be bigger than a small parameter, and then also notice that lambda over omega is represented here, which is also small. So consistent, in terms of consistency, this expression is consistent with our assumptions. All these quantities are small quantities, but so the inequality can be satisfied among those small quantities. The excitation from rest corresponds then to, in this expression, the excitation from rest corresponds to all the region, the region above the hyperbola. This hyperbola for any drive amplitude that is above the hyperbola and any range of frequencies within that region, there is going to be growth. The amplitude is going to grow from rest to some finite value. Okay? Right? So we derived that yesterday. For a given drive amplitude, there is a whole range of frequencies for which the system can be excited from rest. And the range of frequencies for a given amplitude is bounded by these two values, epsilon plus and epsilon minus. So given a amplitude eta, we can determine the values or the range of values epsilon for which we are within the growth region, and that is simply the intersection of eta with the curve that gives us the two values, and they are I have them written here. Notice, of course, that omega naught squared times eta squared has to be bigger than lambda squared for that to have a solution. So what we're going to do today is include the nonlinearity. Okay, we're going to bring the nonlinear term. We obtained this result by because we were dealing with excitation from rest, we were neglecting the nonlinear term. Now we're going to bring it back. And if you recall, when we didn't have the nonlinearity, the equation that we got for the modulation amplitude that modulates this oscillatory term was under the assumption that d chi dt be much less than omega times chi. Under that assumption, we obtain the equation 2i omega d chi dt plus 2i lambda chi plus omega naught square minus omega square times chi plus 2 eta omega square chi over bar. Okay, so that is the right hand side. That is the right hand side. Just shoving in this solution of x that contains this dependence chi e to the I omega t plus its complex conjugate plus higher harmonics, and doing the harmonic balance on the left hand side, we obtain that expression. Now we can continue doing the same harmonic balance on the right hand side. So pick only the terms that goes e to the I omega t. Okay, so this is going to be equal to what? It's going to be equal to whatever is going to result from taking the cube of x. So let's figure this one out. Okay, so by cubing x, we're going to have the cube of this. E to the chi e to the I omega t plus its complex conjugate plus higher harmonics. Okay, we are cubing that. So we just do term by term. Okay, this is going to be equal to chi cube e to the 3i omega t. That is the cube of the first term. We're going to have 3 times chi squared times chi complex conjugate, then is the square of this times this is going to bring e to the 2 I omega t times e to the minus I omega t. That gives us a term e to the I omega t. Okay, then we're going to have a term similar which goes like 3 chi complex conjugate square e to the minus I omega t. This comes because we're taking the square of this goes as e to the minus 2 I omega t times e to the I omega t brings out e to the minus I omega t, etc. Terms that do not pick up an e to the I omega t term, or terms that are very small. Okay, because in the higher harmonics are going to contribute ever so small. So to lead in order, the term that contributes to the e to the I omega t balance, harmonic balance, is only this one. Okay? So essentially we are done by just recognizing that term. And this guy, notice this guy can be written as 3 chi
Absolutely.
Yeah, chi complex conjugate times chi, right? And this is the modulus square of chi. So this indeed becomes 3 alpha chi square times chi. Okay. And the modulus square times chi. So this is the nonlinear equation that we can solve. And we can do it the same way as we can decompose this in its polar form and represent chi as a real amplitude times e to the I, a phase that is also real, and shove it into here. Notice that the nonlinear term is very easy to deal with because the modulus square of chi is a square, simply, right? The modulus square of chi is just a square. And chi is a e to the I phi. So we do essentially the same. We take on the same program that we did for the linear case, for the excitation from rest. The nonlinear term poses no difficulty whatsoever. The only real complication comes from here, but we have dealt with that yesterday. So with the same approaches we have done, and also because it's on your homework, we get the following two equations: one for the phase and one for the amplitude, which are the result of shoving this into this expression and picking the real and the imaginary part. And so we have, for the real part, we have the equation 2 omega d phi dt equals omega naught square minus omega square minus 3 alpha a square. This is a new term that came from the nonlinearity, plus the derived term 2 eta omega square cosine 2 phi. And then we have an equation for the amplitude. dA dt is minus lambda plus eta omega a times sine 2 phi. So what we did yesterday was for the linear case, for the excitation from rest, we didn't have this term. That term was not there. And so what we did yesterday was to look for solutions to these two equations where the phase is constant, okay, without that term, and the amplitude grows. So for which the phase, there's an amplitude here, for which the phase is constant, but for which this term that is on the right hand side is a positive term. The coefficient of the amplitude is positive. So we have growing solutions with constant phase. Now we have a different problem here. We have a problem where in the phase equation there is an amplitude squared. The amplitude equation looks identical to yesterday's problem, but now the difference here is because of this guy, we can still ask for solutions for which the phase is constant and the amplitude is constant. Okay? Such solutions exist. And so that means we are looking for solutions for which this guy is 0 and for which that guy is 0. We unravel this problem by finding a solution for sine of 2 phi. Notice that the amplitude drops out of this guy, finding a solution for sine of 2 phi, putting it in here, and that gives us a relationship between amplitude of the oscillator, the amplitude of the drive, and the frequency offset between them, and the nonlinearity. So let me just plug that in, and that is in your notes in equation 137. Again, the mechanics to get to 137 is set this equal to 0, find a solution for sine of 2 phi in terms of lambda and eta. The amplitude over here drops. Put that solution here into the cosine term, and then you get an expression for the amplitude, and also you can get an expression for the phase. I'm just gonna go ahead and given that this is how chi is expressed, find the steady state solution. The steady state solution. So the steady state solution is one where the amplitude square is equal to 2 omega naught divided by 3 alpha times minus epsilon plus minus the square root of eta squared omega naught squared minus lambda squared. So that is the solution for the amplitude, and the solution for the phase is such that the tangent of 2 phi is equal to plus or minus lambda over the square root of eta squared omega naught squared minus lambda squared. Okay, now lots of things to extract from this information. Is this okay so far? Is this okay? It's algebra. Beyond those two equations, this is just pure algebra.
Yes, but it's not only algebra. I think that it's my problem that I understand a lot of things here, but so many information in those equations that I don't write everything down and then I forgot.
Okay, so where do you wanted me to go back there?
No. It's just
So it is clear. Is it clear that this one was fine, right? Getting to this one is fine. Using this polar form is fine.
Yes.
Putting that and getting the equation for the amplitude of the phase. Then steady state. We want to see steady state. Can steady state be sustained? So that means finding the solutions for which d phi dt is equal to 0 and dA dt is equal to 0.
Yes.
And those two, then it just turns into algebra.
Okay.
It turns into algebra where we had made the approximation again that omega is not very different from omega naught, differs by epsilon, and so we can, whenever say we have something dividing by omega, we just replace it by omega naught. But when we have the difference omega minus omega naught, we replace it by epsilon. Okay, so and that's how this expression comes to be, where from the amplitude equation we find the solution for sine of 2 phi. It's very simple. Sine of 2 phi is simply the ratio of lambda to eta omega naught, right? And then substitute that into the equation for the phase and find what is cosine of 2 phi that way. And then we can get an expression for the amplitude. So this gives us the steady state solution. And notice that the following. If I multiply by alpha, let me actually multiply by alpha because I want to take the nonlinearity to 0, okay? Want to take the nonlinearity to 0. If I take the nonlinearity to 0, okay, then that means that the expression in the brackets is 0. That expression in the brackets being 0 corresponds to points along the curve. So everywhere when the nonlinearity is 0, the only steady state solutions that I can get are the ones for which that exist along this curve, for which the drive and the frequency difference between drive and natural frequency match. Okay, all along this curve, I can get steady state solutions. Also, in the linear case, the steady state solution is dA dt equals 0. But in the linear case, they can only be met here. In the nonlinear case, when alpha is not 0, even when I am in what was the growth region, I can get a steady state solution, because as I mentioned to you yesterday, that is equivalent when the amplitude grows, the nonlinearity set in, and that is equivalent to the shifting of this curve. So if I'm at a point right here that would be growing in the linear case, nonlinearities kick in and shift the curve so that this point eventually meets the curve. Or depending on whether it's alpha is positive or negative, the shift can be to this direction or to that direction. So nonlinearities are acting as a way to always get us on the curve in this parametric space. This is the space of eta and epsilon. It's a parameter space of the drive. It's not the response space, but the parameter space. So in the parameter space, nonlinearities move the system to the curve, or move the curve so that that point lies on the curve. So steady state can always be met by nonlinearities. You get a different point, that will give you a different amplitude of response, and that will give you a different location on the curve. Okay, so this guy guarantees steady state, but not for all values of the amplitude. Let me take the case when the amplitude, or rather when alpha is positive. When alpha is positive, then in the absence of drive and dissipation, when I don't have a parametric drive, so when eta is equal to 0, and when lambda is equal to 0, I'm then reduced to the problem of a free nonlinear oscillator. When alpha is negative, rather positive, and eta and lambda are 0, then I get an expression between the amplitude of the response and the frequency difference between the natural frequency, natural linear frequency, and the actual frequency of oscillation of the say the pendulum, which is represented by this curve. So notice that this is the same result we have already obtained in the past for a free nonlinear oscillator. The frequency difference, epsilon, which is omega minus omega naught, is equal to 3 minus 3 alpha a squared over 2 omega naught squared. That is a result that we have gotten in the past. So this is an identical result. We'll recover the freak oscillations case when eta and lambda is equal to 0. But when eta and lambda are not equal to 0, the relationship between amplitude and frequency difference follows this particular curve. Okay, so let's trace it. Yes.
So how does from the steady state equation over there? How then over there we have an omega naught squared.
Did I get an omega naught?
Where did that come from?
Oh, I'm sorry. Did I get? My mistake. This should be omega. My mistake. That should be omega. Okay. That should be omega. Okay. So let's look at this curve. Let's look at this curve and let's go to the demo. So if I start from out here, okay, and I drive with this frequency, I pick an amplitude of the drive. Pick an amplitude of the drive, okay? and then I start out here, then my response is gonna be 0. That's Bruce. My response is gonna be 0, right? There is no response amplitude. Okay? Then I hit this value right here. At that moment, the amplitude of the system starts to grow, and then nonlinearities take over. As I decrease the frequency of the drive slowly, then the amplitude of the response goes along this curve. Okay? And I keep decreasing, continues increasing. There is going to be a point where the amplitude when the frequency reaches a value where such that if I reach that point, there is a sudden drop. Okay? And then if I continue decreasing the frequency, I go nowhere. The response continues to be 0. Then if I increase it, okay, back over here, there is going to be a point right here where the system picks up again. But it doesn't go anymore, it doesn't go along that aspect of the curve. Actually, this part of the curve is never realized. It's a metastable state. So rather than picking this one, the system jumps to this place. So right here, I have a hysteresis loop again. Okay, let me show you the hysteresis loop. It's like a little more visible in this case than it was in the driven case because of the nature of my system. Has a little more damping and it helps a lot. So I'm gonna start at a frequency that a fluctuation is gonna bring it, say, to some point over there. Okay, and then I'm gonna be decreasing. As I decrease the frequency, I'm gonna climb up, and then there is gonna be a frequency beyond which it just jumps down. Okay, so let's see. Okay, so I started right there, 2.67 hertz. Okay, 2.67 hertz. Now I'm gonna go down in frequency, and I want you to look at the amplitude. 2.66, excuse me, 3.67, 3.65, 64, 63, 62. I don't know if you can see an increase in amplitude. 6.1, 5.9, 5.7, 5.5, 5.3, 3.51, 3.49, 47, 45, and clearly the amplitude has gone up. So I'm climbing up here. 5.3, excuse me, 4.3, 4.1. So that's 3.41 hertz. 3.9, 3.39. 3.7, 3.5, 3.3, 3.1, 2.9, 3.29, 3.27, 2.6, 2.5, 2.4, 2.3, to 3 to 2 to 1 to 0 3.19 0.18 17. I'm getting there. That's why I'm going very slowly now. I'm there. So you jump by 3.8, between 3.18 and 3.17. Okay, just went down. Okay, it's pretty clear, right? The jump was clear. Now I'm gonna go up. I'm gonna now move this direction, and in these steps I'm gonna be kicking a little bit the pendulum just to explore that steady state and see if it can jump up. Okay, so I'm helping it because as you notice, the damping is big. So I'm gonna increase now a little farther. Say rather than steps of 0.01 hertz, I'm gonna be 0.05 hertz. So right now 3.17. Let me go to 3.2. Okay, let's give it a kick. That guy dies down, okay, clearly. At 3.2, that was way out here, okay? So let me go to 3.25. Okay, again, nothing there. 3.3. Dies out. 3.35. So dies out. 3.4. Okay, that died out. 4.5. Let me give it a little more. 5.0. And I got it right there, right? I think. Yes. So I reduce it every time I give it a kick. It didn't quite make it. I had to actually bring it to this region, to inside this region. And so right inside this region, I gave it a kick and moved to the place where it belongs, on that curve. Okay? Now let me change the demo. Let me change the demo. In this demo, I have the pendulum increasing its amplitude as I decrease the frequency. That was for a fixed drive amplitude. By the way, this region here between epsilon plus and epsilon minus is the same region here between epsilon plus and epsilon minus. It is for a given drive amplitude that defines the region epsilon plus to epsilon minus, or epsilon minus to epsilon plus. So I was coming from here. I was not inside the growth region coming out here. Once I hit this spot, I reach the growth region. The pendulum can now be excited from rest and then reach a steady state. Okay, so what I have in the parameter space, I also have in the base of this nonlinear tuning curve. Now what I'm going to do is increase my drive amplitude. If I increase my drive amplitude, I increase the range of drive frequencies. Okay, but look what happens. I increase my drive amplitude, I increase the range of drive frequencies. That means eventually the amplitude is going to be big enough that it's going to be hitting the sides of the speaker. Right? So it becomes a different oscillator at that moment. before it hits the size of the speaker, is just a pendulum that whose frequency decreases with whose amplitude increases with decreasing frequency. Okay, the amplitude increases as I decrease the frequency. When the pendulum hits the cone or the walls of the cone, then it becomes, it's an oscillator that is hitting a kind of like a rigid wall. So the frequency of oscillation now is gonna, or rather the amplitude is gonna increase with increasing frequency, because now the system becomes hard. It becomes almost like a free particle hitting two walls. Okay, so what determines the frequency of oscillation? The speed of the particle. Okay, I increase the speed of the particle, then the particle bangs back and forth faster as I increase the velocity of the particle. Yes, so that's what is going to happen. Let me lower my bouncer here. I was worried in the previous demo that the pendulum was eventually going to reach that spot. So what I'm going to do is go up in amplitude so I can reach the end. Let me go up in amplitude, say to there. No, actually more like there. And I'm going to reduce the frequency. Actually, let me make it a little bit. So I'm going to reduce the frequency. I'm at 3.5. 5.9. 5.8. Excuse me. 4.9, 4.8. 4.6. 4.4. 4.2. 4.1. 3.9, 3.7, 3.37, 3.5, 3.3, 3.1. Remember when did the other guy fell off? In 3.17, right? 3.1. Now I have increased my amplitude. 3.1, 3.0, 29. 28, 25, 21, 20.
Stop.
I want it to bang in both sides. $3.19, 17, 16. Okay, let me go back in frequency. Let me go up in frequency again. Let me up the amplitude. Okay, 3.33, 3.1, 2.9, 2.7. Now that I reach that, I'm going to increase the frequency. Because remember, once I have a particle hitting the walls, increasing the frequency amounts to the particle speeding up, okay?
Hitting the wall was like damping?
Huh?
Hitting the wall is like a damping effect?
No, it's actually it's a stiffening effect. It makes the springiness hard, okay, because you're hitting the wall. So higher frequency corresponds to higher amplitude in a sense, because it's faster, the velocity is bigger. So I'm increasing the frequency now, 3.3, 3.5, 3.7, 3.9, 4.1, 43, still going on. 45, 3.45, 47, 3.50. Remember, 3.50 was a lower amplitude, right? So let me actually try it. Right there, that was 3.50. Oh no, let me try it again.
You're at a higher amplitude now. Than you were back then.
Yeah, let me go to 3.55. So that's one state of the system, okay? And that is another state of the system. Okay, so what is it doing? Once it reaches the wall, this guy turns to the other side, actually very flat. Okay, so now as I increase the amplitude, as I increase the frequency, it keeps banging the walls. And so there are two states for a given frequency, this one and that one. So I'm increasing the frequency more, 3.57, 3.6, 6.6, 6.8, 3.7. So I have that state again. And that state. Two states, okay? That and that. Which are explored according to initial conditions. Okay. Happy with that demo? It's not all. There's more. No. Now this is an inverted pendulum, right? You know what happens with an inverted pendulum. This is an equilibrium point, right? The pendulum being upside down is an equilibrium point, but it's an unstable equilibrium point. It can go one way or the other, right? You can just climb off that potential well one way or the other, depending on the fluctuations. But imagine doing the following. When the pendulum wants to go this way, you pull it down, so it wants to climb back up. When it goes this way, you want to pull it back up. But because this is a very unstable equilibrium point, the rate at which you have to pull back in has to be very fast, and the excursion amplitude has also to be very fast. You have to essentially on that potential maximum, you have to create a minimum, okay, by driving the point of support. So this is what we've done. We've done only one of those regions. We've done this place here. Let's see, right here. That's where we have calculated that hyperbola is right here. This region is an unstable region. Those correspond to stable regions. This is a slightly different plot that we have done. This is almost proportional. This is actually proportional to the drive amplitude, and this is proportional to the drive frequency, except that it's goes as the inverse of the frequency. square. Okay. Now notice that there is a region here. There is a region right there that is stable. All these shaded regions are stable. This is particularly interesting, the fact that there's a stable region where this number 2f naught over f squared is negative. 2f naught over f squared being negative corresponds to an f naught that is an f naught squared that is negative. That is the inverted pendulum. Okay, the inverted, when the pendulum is upside down, omega naught is negative. When the pendulum is side up, omega naught is a positive. Omega naught squared is a positive thing. So it's a positive down here, but it's negative down there, because down here is the potential. You have a potential that has a minimum. Up here you have a potential that has a maximum. So omega naught squared is positive here, omega naught squared is negative there. So that region exists in the inverted pendulum. Let me get there. Let me now drive it. Notice that I have to drive it very hard, because this is a very small value, very little off the origin. So I have to drive with a high frequency, and I also have to drive with a high drive amplitude, because again I'm dividing by that term. So let me explore that. So my inverted pendulum is going to exist around 9 hertz. I was driving, around 25 hertz. Remember, I was driving around 3 point something hertz for the side of pendulum. For the inverted pendulum, I need to go to about 25 hertz.
Will it be stable?
Huh?
Will it be stable?
Yeah, you'll see.
It's perfect.
25 hertz, okay? And then, but I also need to drive a very high amplitude. Okay, so that, you see, that is 25 hertz. You see the speaker, the diaphragm of the speaker. So let me bring my amplitude. Right there. Notice that it's stable. And a test of the stability is to move it about it. If it is stable, it's going to oscillate about that stable point. Okay? I'm going to turn this off because I really care for this speaker.
Would the frequency will be the same if we have with the pendulum we have more degrees of freedom, like it was like something like this?
So, right, you still have a maximum in all directions. Yeah. So, I likely it would, because if you drive only vertically. Oh, wait a minute. It might actually be preferential, right? Because notice we were driving. No, it would not be preferential. Just driving the point of support. Any direction is possible. So the frequency might be the same. The amplitude might be different. But this is a case. You know, this is a case that actually pictures in chaos. Okay, because the system can go right or left, can quickly depart from its equilibrium point, very quickly, exponentially depart from its from the condition of zero velocity, zero amplitude, and either to the right or to the left, depending on, is sensitive to the initial conditions. There is an unstable point. In chaos, chaos is rooted in unstable points. Unstable points drive chaos out, or drive chaos into the problem. But if I turn the unstable point into a stable point, like this case, right? I remove chaos from this problem. So chaos, as we will see, is driven by unstable points. and we can bring the unstable points to become stable points by driving around them. Okay, like what we did right here. So it's there are lots of demonstrations that address that issue. I remember one where you have they had a rod that also was shaken, and the rod would undergo flexural modes, but it would be standing upright. Okay, so you can stabilize on stable situations with a parametric drive like this one. Okay. All right. That's that for tomorrow. I'll show you just a collection of demonstrations on maintained oscillators, and I'll just motivate the topic. We would not spend any time, actually zero time, doing, well, maybe a couple of minutes doing a little math, but just to map the problem into certain class of oscillators. And the maintained oscillators are present in a lot of aspects of physics, and I'll illustrate those one at a time. Okay.